Oops, wrong screen. Sorry. Yeah. Hmm. Okay. So, yeah, uh, yeah, this one. Yes, correct. Today we'll discuss about the chemistry of resin polymer, and this discussion. Yes. The objective of this lecture is to introduce you to the basic of polymer chemistry. There are types of polymers, and their properties, applications, and so you can recognize polymeric materials in dentistry and know their functions. So the content of this lecture would be a short introduction, and then the polymers and their properties, and the polymers in dentistry, which includes acrylic resins, heat activated resins, light activated resins, and chemically or self activated resins, which were already discussed during our uh, lab practice substitutes last week. So let's go back a little bit to the type of materials. We have three different types of materials generally, like ceramics, metal, and polymers. And if we look at the stress strain curve here, we can differ them distinctly by the strength of the material. So polymer has the lower strength of all the three types of material. However, they can undergo very large deformation, and thus they do not break easily. And for the opacity, polymers have better optical properties compared to the ceramic and metals. However, the conductivity of polymers is very low, and in biomaterials, we need biocompatibility for their applications in their host. So the main properties of polymers. Let's talk first about the drawbacks or the disadvantages of using polymers in biomedicine or biomedical sciences. They're not as strong as metals, and they quickly deform when the load is much higher than their yields. And the last one is they can undergo degradation, much prone to degradation compared to ceramics and metals. However, when we talk about polymers, we have something that the other two do not offer. polymers are resilient, meaning they do not break easily, although they deform. And then they are easier to process, to manipulate, to create the end products of the intended application. And last thing that is also the most important things in dentistry is their colors or their aesthetics, because sometimes we need some clear and shiny and translucent or transparent materials for application in dentistry, especially when we need something to do with the anterior teeth. So we use polymeric resins, not metal, not ceramics, although some ceramics are also used in uh, restorative dentistry or prosthodontics because they have better properties. However, they break without notice, meaning they're not resilient, they're brittle. A little bit about the history of polymers in dentistry. So more than 2,000 years ago, the first materials, biomaterials used in dentistry was gold or gold leaf to be precise, used to fill the hole in a tooth. So they acted as dental fillings. And then few decades later, ivory was used to replace some tooth. So they acted like ivories acted like prosthetic. And then the first polymer in dentistry was PMMA or polymethyl methacrylate, introduced in the first half of 20th century. I think it was around 1940. And then polymers were developed further, and thus we have now PET or polyethylene terephthalate, and then PE or polyethylene, and some other advanced polymer like ether ketone, and so on. So, can anyone describe the definition of polymer?
Perkumpulan dari beberapa monomer.
Yes, perkumpulan, himpunan, BEM, kemahasiswaan. So polymers are large molecules composed of small molecules called monomer. And if we look at this image, we can recognize the monomer. So the monomer of this polymer is like 1, 2, 3, 4, 5. What is it? C5 is pentane. Yeah, pentane. So one is methane, ethane, propane, butane, pentane. Okay. However, we have oxygen here, so it's I think it's carboxylic acid. Yeah. Or then we have repetition of this monomer, making a large polymer. So it's already mentioned that the small molecule is called monomer, and then nowadays they are most likely synthesized from oil, like polyphenol chloride, polyethylene, PTFE or Teflon, and then PMMA. And we also actually have some natural polymers like rubber and alginate. However, in this discussion, we will only discuss the, the, the synthetic polymer, which are used in dentistry for dental filling and biomaterials. Unlike the natural polymers like alginate and rubber, they're used as supporting or auxiliary materials like impression materials and uh, negative molds, etc., etc. Here, the polymers are used directly as biomaterials in the oral cavity. So the the fundamental properties of polymer, first thing you need to know is polymerization. So when we have one monomer here, one monomer called two carbon means ethena. If it was single bond, it's ethana, but it's here double bond. It's called ethena. When we break this double bond, the ethane would be radicals. Would have two radical carbons, which then they would react with each other, creating a chain reaction that further lead to polymerization, and thus here we have polymer. So double bond broken down, radical, and then they react with each other and resulted in polymers. So the general steps in the polymerization already discussed during the lab substitute. So the first step is initiation, creating free radical, and then propagation or the lengthening of the polymers, and then termination or the ending. So 3 steps: initiation, propagation, termination. Initiation meaning creating free radicals for the chain reaction, and then propagation is the chain reaction itself, and termination is the ending of the chain reaction. Could happen naturally because all the monomers are gone, or we could also stop the reaction by adding some additive material to stop the propagation. However, it is rarely used in dentistry because we do not want to leave any monomers in the bulk body of the polymers, since they could exhibit toxicity. So we just let all the monomers convert into polymer. So there are some routes of polymerization. First one is addition. Addition meaning to add. When we have one, what is it? No. Ethane with one moiety or functional group, the double bond will break, and second polymer with very similar characteristic, which also has one double bond, they will create a copolymer. So here we have R1 and here we have R2, and thus the polymer resulted in this reaction would be R1, R2, R1, R2, and so on, with the number of N plus M repetition. We have M number of R1, N number of R2, and here we have M plus N. Yeah. And then second route of polymerization is called condensation, which create a byproduct when we react ester here with the diol meaning an alcohol with two hydroxyl group. They will create this type of polymer. So we have this N plus R2. However, the hydroxyl group from R2 and R1 are combined and creating a byproduct of water. So actually, if we look at these two types of polymerization routes, we can already decide which route is better. So, which route is better for our needs in dentistry? So here we have a byproduct of water, which would create void. Okay, void, because water does not contribute in the strength of material, and in contrast, it will contribute to creating bubbles and voids, and thus addition route is much better, because the addition route does not create byproduct. There are some hindrances in polymerization, like impurities that may react with free radical or the initiator of the polymeric chain reaction. However, impurities are also intentionally added to prolong the shelf life and avoid self-polymerization. For example, hydroquinone here is used to inhibit self-polymerization. Some polymers can undergo self-polymerization because their shelf life, they will by themselves react without any initiation. And exposure to oxygen can also hinder polymerization. And that is why one of the main drawbacks using dental filling, polymeric resins for dental fillings, we need to really clean the surface of the tooth, so there is no water in the tooth, because water can contain oxygen, and oxygen will hinder the polymerization. What about the oxygen in the air? Yeah, they also react. However, without the presence of water, the reaction is so slow because the the surface area of the active polymer and oxygen is very low. And then we may also add a plasticizer to reduce melting point and to make polymer more flexible. So here we have different types of polymers, like I mentioned in the previous slide. Uh, Based on their sources, we have natural polymers like protein, polypeptide, latex, polysaccharides, and carbohydrates, but they are not used for biomaterials, of course. And synthetic or man-made polymers like PVC, polyvinyl chloride, polyethylene, polystyrene, Teflon, and PMMA, uh, they are used in dentistry. And if we look at their physical properties, like their responses to heat, we have thermoplastic and thermoset. Thermoplastics responses to temperature, rising temperature by softening. So when the temperature is raised, they will be softer and they will melt. However, when we cool the thermoplastic, it will go back to the solid form. And these reactions is reversible. So you can heaten the thermoplastic to melt it down and then pour it into some mold to create some specific shape, and then cool it down and let it rest to let it harden to the intended shape. However, it is very different with thermoset. The thermoset polymers are softened when heat is applied until critical temperature. And then when we remove the heat, they will harden. However, when we apply more heat, they will not uh, they will not be softened anymore, and thus this reaction is not reversible. So some example of thermoset polymer like uh, plastic steel. Does anyone know plastic steel? Plastic steel, steel meaning baja. Yeah. So you add two different compounds, and then during the mixing, it creates they create some heat, and then after that you let it rest, and then yeah, they just set. They would not uh, they cannot be back to their original form of liquids like thermoplastic. And when we talk about the properties of polymer, we need to address their molecular form. Like here, we have linear polymer, branch polymer, crosslink, and network. So, judging from these images, which polymer has the highest strength? Anyone? Zaki? Cecil? No? You discussed a lot about the polymers in our previous activity. So I think you should know. Okay, so if we look at their structures, the strongest polymer here is network polymer, because they have more bonds in their molecules. And then we have crosslink polymers, and then we have linear. Why linear? Why not branch? Because the branch polymer has some steric hindrance, so their single chain is larger than the linear polymer, which create spaces between their single molecule, and thus their mechanical property or their strength is lower than the linear polymer. Why linear polymer is stronger than the branch polymer? Because they're linear, they can be in very close proximity and create secondary bonding, either van der Waals bond or hydrogen bonds. However, when we cross-link these branch polymers, we can obtain much stronger polymer compared to the linear form. So in their own form, network is the strongest, and then crosslink, and then linear, and then branch. But when we crosslink the branches here, yeah, so crosslink branches, cross-linked branches create stronger polymers compared to the linear. And yeah, the longer chain, the stronger, because of the secondary interaction of these functional groups or moieties, or the proximity or the surface. Let's dumb it down to surface area. So the largest surface area, the stronger. Okay, so the longer the chain, the stronger the bonds. However, like I mentioned before, branches reduce crystallinity and thus weaken the linear polymer. And then to overcome this situation, we can do covalent cross-linking to enhance the strength and increase the melting point, and thus we have a stronger polymer. And in addition, the polarity of the side groups also increase the strength, because sometimes side groups of polymers, or the functional group of the polymers, may obtain some chemical characteristic. Like I mentioned before, they can interact with each other to create secondary bonds, like van der Waals or hydrogen interaction, like this one. So in the right hand side figure, right hand bottom side figure, you can see some hydrogen interaction here, here, and here. which creates stronger polymer compared to the um, linear polymer without side groups. Second thing is the molecular weight. So practically, we cannot define the exact molecular weight of a polymer. So the ideal polymer should have very narrow molecular weight distribution because meaning it could mean the size of every single molecules are the same, the length of the chain of the polymers are the same, and thus the molecular weight is very narrow, very uniform. However, to date, we cannot produce that kind of polymer, and the approximation only could create this narrow a polymer with narrow molecular weight distribution, and most polymer also have this kind of molecular weight distribution. So if you let's say if you want to perform some experiment in laboratory, you need to buy a polymer, let's say polylactic acid or polylactic glycolic acid or polyethylene or something else. The manufacturer will give you information regarding their molecular weights, but not the exact molecular weight. They will only state the approximate molecular weight, like it's around 2,000 kilodalton or 30,000 kilodalton, something like that. So actually, it's when they say 30,000, it could be 29,000 to 31,000 kilodalton, like in a range, not exact points of molecular weight. So yeah, it's non-definite. It's a range, not an exact point, and the stated molecular weight is the z average of the by molecular weight by distribution. Distribution, sorry, molecular weight distribution. Yeah, because the length or the number of the repetition is not always the same in every single chain of the polymer. And I mentioned copolymer in the previous slide. So when we have polymer, we could have homopolymer or polymer with same repeated monomer. What about different monomers? We could have copolymer, like the most popular one is PLGA or polylactic co-glycolic acid. They are extensively used in biomedical engineering to create scaffolds, network supports for cells, etc. And yeah, when we talk about the copolymer, there are some different kind of copolymers. Like the very simple one is alternating copolymer. So we have monomer A, monomer B, A, B, A, B, A, B, and so on. It's alternating copolymer. And when the arrangement of these two monomers are not in good sequences, we call it random copolymer. A, B, A, B, B, A, B, A, and so on. However, when they're arranged in group manner, like this, A, B, 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 it's called block copolymer. And then we have one other polymer called branch or grafted polymer. So the main backbone of this polymer is repetition of monomer A. However, then we add B to create branches, which may also react with the other this polymer, creating backbone A over here, and cross-linked by B. Something like that, yeah. And next characteristic of polymer is called tacticities. Let's say we have some polystyrene here. Polystyrene ethane with a phenol group here. Sorry, a benzene ring, not phenol. So when we make a fissure structure of this polymer, like this, like a ladder, we may want to know where exactly the benzene ring is placed. So when we have the structure of the benzene ring all in the same side, it's called isotactic. Iso mean same, isotactic. So they're all in the same side. However, when the benzene rings are placed in alternating way, it's called syndiotactic. And when they are placed randomly, it's called atactic. A mean not like in abnormal, not normal. Here, atactic, not tactic. So isotactic, syndiotactic, and atactic. Yeah, crystallinity. So no material in the world can reach 100% of crystallinity, including metals and glasses. They contain small portion of amorphous constituent in their bulk material. And in polymers, we have both amorphous and crystalline bodies in the bulk body of the polymers. So polymers cannot be 100% crystalline for sure, but they may contain crystallinity. So if we look at the arrangement of these molecules, this is randomly placed molecules which create different gaps between each molecule. And defining this situation, we call it amorphous site. However, when the molecules are placed in a neat way, arranged properly, very closely, very packed, we may have some higher crystallinity. So here amorphous, here amorphous, here amorphous, here crystalline, because they're arranged in a very neat and close pack. Here also crystalline. And when heat is applied to the amorphous phase, the amorphous phase of the polymers will undergo glass transition. In contrast, the crystalline phase will melt because it's already in their strongest condition. So amorphous phase will undergo glass transition, or let's say rearrangement of their molecules to create better crystallinity. But the crystalline phase, since they're all already arranged in a neat way, they already reach their highest strength, and thus they will not rearrange themselves but melt. Also, the amorphous phase, after they arrange to glass transition, they will achieve higher crystallinity, but then again, they will melt. So here is the illustration of what I discussed earlier about the glass transition and melting of the crystalline polymer. When we have higher crystallinity, we have higher stiffness or Young's modulus, or modulus of elasticity, meaning they require higher load to be broken down. And to reduce their strength, heat is sometimes applied, and then they will undergo glass transition and then melt. But then in some polymers, like in thermoset, the reaction will not further break down the polymers, and it will just create a situation where the polymers are just set and not melt further with increasing temperature. Okay. In dentistry, we have some types of polymers like resins polymers and elastomers. However, like I mentioned before, the elastomeric, elastomers like silicon, polyether, polysulfide, they're not used as biomaterials. They are only used as supporting or auxiliary materials to create the biomaterials like denture bases, crown, dental fillings, etc. And polymeric resins used in dentistry includes acrylic, like heat activated resins, light activated resins, and chemically or self activated resins. So acrylic resins is mainly polymethyl methacrylate or PMMA that has been used since 1940. This is the structure of methacrylate. When we repeat this, create polymethyl methacrylate. This is methacrylate. This is the methyl. So polymethyl methacrylate. So when the PMMA set, PMMA is biologically harmless because they're not soluble in water. They do not dissolve in water. They do not release substances in water. However, when we have PMMA in their liquid or powder forms, they may exhibit cecity. They may exhibit carcinogenicity. But once they set after the reaction of polymerization, they are fully safe to use as biomaterials. Yeah, acrylic resins are used due to their excellent balances of hardness, flexibility, and durability, and easy processing and handling. And then one of the most important things in prosthetics is their versatility in their optical properties. So, like I mentioned before, acrylic resins are formulated in liquids and powders with small amount of hydroquinone. So, does anyone still remember what hydroquinone is used for in acrylic resins?
Inhibitor, Pak.
Yes, exactly. It uh, it is used to inhibit self polymerization in acrylic resins. So the first type of acrylic resin, which we will use on Wednesday for our lab activity, is heat activated resin. So the heat activated resin is composed of methyl methacrylate and glycol dimethacrylate. The glycol dimethacrylate will cross-link the PMMA or polymethyl methacrylate, creating stronger polymers compared to their initial form of PMMA and glycol dimethacrylate themselves. What is the activator or the catalyst of this reaction? Alifa? what is the initiator or the activator of this reaction? I'm already pointing the clue here.
The heat.
Yes, the heat. That is why we call this type of acrylic resins heat activated resins. They may also react naturally without heat, but it will take a very long time to let the reaction complete and have fully set acrylic resins. So second is light activated resin. I remember Cecil mentioned something, mentioned a lot about this light activated resins. We have camphor quinone here as the initiator, which is activated by light. So the camphor quinone will then attack the DMA to create complexes, which further create chain reactions of polymerization. So, does anyone know why the light activated resins are stored in black or dark container? Why? Why light activated resins are stored in black or dark container? Nadine?
Izin menjawab, Pak. Maaf kalau salah. Light activated resins itu stored in black or dark containers to prevent accidental exposure to light.
Yes, correct. So actually, the light activated resin can also react. Sorry. The camphor quinone can also be activated to create radical foam by the natural light like sunlight or even the light from light bulb. However, here we use blue light, specifically blue light, because it has the exact amount of energy needed to create the radical forms of camphor quinone, which further initiate the chain reaction of polymerization. So the advantages of using these light activated resins include low porosity because they don't leave monomers unreacted, and then stable optics. That is why light activated resins are commonly used in dental fillings, and controlled working time, because when we when we still need to work on the shape of the material, we just leave it without light, and then after we are sure that the shape is correct, like when we need to form fissures, cusps in molar teeth, using this resins, we just wait until the foam is settled, and then we apply the light. However, they also comes with some drawbacks, like limited curing depth, which is a maximum of 2 millimeters. And if we do not control the application of this light activated resins, when we add too much resins in one go, which create bulky materials. Once we apply the light to initiate the reaction, since the original foam without activation is so large, they will undergo shrinkage, which further create residual stress. And this residual stress weaken the bonds between the dental fillings and the filled tooth. And weakened bond can lead to porosity, to gaps, and then attracts bacteria, and then secondary caries, etc., etc. We need to replace the dental fillings again. Oh, sorry. Yeah, I will just go. So last type of resins used in dentistry is chemically or self-activated resins, but I think now we rarely use it due to too many drawbacks, like the use of amine accelerant, which is not very comfortable for patients because of the smell. And then unreacted monomer can be very irritative. And then the unreacted monomer also creates high porosity, high residue, and low strength. So compared to light activated resins and heat activated resins, chemically activated resins are no longer used. And I think on Wednesday we would perform this molding technique, compression molding, by first we prepare the acrylic resin by mixing the powder foam and the liquid foam together. And then after they reach dough state, we place the resins in the mold, and then we compress the mold, and then we apply heat by boiling in water to accelerate the reaction. Yeah, but do not forget, before applying the acrylic resin, we need to apply some sealant to ease the removal procedure after the denture base resins set. So this one is already discussed in our previous meeting. The ratio of powder and liquid is usually 3 to 1 to maintain the high yield of reaction and to avoid shrinkage. And there are 5 stages, or let's say 4. You mentioned four stages of polymerization steps in heat activated resins. So the first stage is sandy, when we have unreacted powder. This occurs when we just mix the powder and the liquid. Over time, it will create a stringy forms of both powder and liquid. So stringy, like something sticky, and then over time, they will be dough-like, dough, and increase consistency, and then rubbery. And then after rubbery state, they will reach the stiff or the end point, which we will further use as the biomaterials. So at the dough-like consistent or dough-like stage, we pack the polymers in the mold. So I think that is all from me today. I guess you are all already know, since you have already presented last week. But if you have any questions, please.
Jadinya tuh dia belum ngelakuin tesnya, tapi dia udah terima duitnya. Si Mr. Sheldon tuh kalau misalnya mingguan sama deh.
You want any question?
Kalau misalnya di apa yang si jasanya ini yang si Miss Apple yang ini kalau di Indonesia ini kalau di berarti
No question. So I take it that you already understood most of it, but if you have something unclear with my presentation, you can just text me or email me for the questions. Okay, so that's all for today. I wish you a good day ahead. See you on Wednesday on the lab activity. Assalamualaikum warahmatullahi wabarakatuh. Good day, everyone.
Thank you, Dok.
Thank you, Dok. Thank you, Kak.
udah berapa lama lo lagi gak? Luas kah atau mau apa? Jam 4 ini kamera video. Hah? Berapa lama? Sekalian lah. Cuma terjawab. Jam 4 masih lama. Parah. Pakai kok. Dulu ini enggak ada. Hah? Enggak ada. Mengatur. Suruh gua ngaku banget yuk. Tidur. Gua kemarin belum tidur. Kemarin gua nggak bisa sama sekali. Kalau dari jam 3 ke jam 8 pagi. 8 pagi terus lanjut jam 12 langsung pagi ke Bandung. Jam 12 pagi ke Bandung. Motoran. Gue foto itu. Oh iya. Itu belum tidur, gak semua buat isi kaca belum ada tidur. Belum ada tidur. Lanjut balik. Lalu nyetir balik. habis balik ngobrol lagi ngobrol. Oh iya, aku ngobrol anjing. Keluar dulu. Disuruh ngobrol modul lagi. Modul itu.
Oh, sebelah kan ada. Sebelahnya ada si A.
Mana katanya nugas. Mana katanya nugas. 2015 sih. Lu tugas apa mana? Pun 2000 ya? Oh, yang pengatur. Aku merasa mereka apa lagi? Orang-orang minta gua.
Ini kerjanya santai.
Ini masih ragu kan?
Masih rapi untuk kan? Selesainya, deadline-nya.
Ini 2009.
Oh iya, ini si. Oh ya kemarin.
Ini pengatur.
Iya, lu referensinya dari mana sih? Referensinya dari mana?
Bikin. Kan dia udah ngasih contoh. Dari contoh itu ini 101 itu harta lancar, 101 itu harta tetap, 121, 121, oke 10 dan angka belakangnya itu harta lancar, 101 itu harta tetap, 12 itu harta tidak berbentuk, 21 utang jangka pendek, 22 utang jangka panjang, 31 modal, owners capital, 32 311 owners 332 itu owners growing, 301 service revenue, 501 itu bebas pokoknya, 501 pokoknya ini ada kalau di expense yang penting expense paling terakhir itu miscellaneous. Kalau ini cuma buat yang di lab doang, kan beda sama atasnya. Ini yang lo hafal itu aja. Kalau misalnya satu depan satu kosong itu apa lo tau ada apa aja. Terus satu ada tetap, 12 tuh harga berbentuk saham sampai aja.